Well, good morning, class, or good afternoon, depending on when you're joining us. Welcome to our first full week of school. We're kind of more on our normal time schedule here, and we're going to quickly look at a couple math notes that occurred last week in our book, and then I'm going to introduce an activity that we're going to do to help us kind of practice what we call the multiple representation of functions, looking at functions and the relationships in lots of different ways. So let's first of all start with this idea of the absolute value. So the absolute value is the numerical value of a number without its sign. So as they're explaining below here, you could have the number like 2, right? The absolute value of 2 would be just 2, right? The absolute value of negative 2, right, would also be 2. And I like how they also say this when we're using these vertical bars. But absolute value can represent the distance on a number line between a number and 0. Since the distance is always positive, the absolute value is always either a positive value or it could be 0. The absolute value of a number is never negative. So this is pretty straightforward, right? I encourage you to look at that. One thing that I've seen is sometimes students will see an expression like, for example, if I write the absolute value of 3 minus 7. So you can see here we're taking the absolute value of an expression. Well, before I do that, I need to evaluate what's inside of the absolute value, and then I will consider the absolute value of that. So 3 minus 7, I've got 3 and I take away 7, is the number negative 4, right? Negative 4. So 3 minus 7 is negative 4, and then the absolute value of that is 4, right? It's 4 away from 0. And again, I think the problem that I see is sometimes students will think whenever they see these absolute value symbols that these negative symbols just magically change to positive symbols wherever they're at. And that's not the case, right? Evaluates what is inside of the absolute value expression and then take the absolute value of that. Another place where I see some error is if for example, we had like, let's say we've got 5 minus, and then we have the absolute value of negative 3. So if we look very closely at this, right, the first thing we're going to do is there's nothing inside the absolute value to evaluate. It's just negative 3. So I can take the absolute value of negative 3. So this expression becomes 5 minus, and the absolute value of negative 3 is 3, right? So this is 5 minus 3, which equals 2. Okay, the absolute value symbol has no effect at all on this fact that this is a subtraction problem. We're talking about the absolute value of the thing that lives inside of those. So that's the absolute value, and we'll keep practicing those and thinking about the meaning of those. The other thing is here is this idea of families of functions, and we're going to be looking at a couple families of functions today, so I wanted to talk about some of these. So one family of functions is the linear family, or linear functions. We're going to look at that a lot during the first semester, and a lot of intricacies, some things we may not know about it, some things we do know. Linear functions have a graph that is a straight line. The line may or may not pass through the origin. So just because it's linear doesn't mean it has to pass through this point, right, on a graph. That point, right, where the x and the y axis meet is called the origin, and they don't have to go through that. However, and let me read the rest of this. The line may or may not pass through the origin, and it may be increasing or decreasing as you read from left to right, right, as I go from left to right. Another function family is called direct variation. So this is a lot like a linear function, right? Direct variation. You can also call this direct proportion or proportional. Now, this is something that earlier on last year you would have studied quite a bit in the 8th grade. Proportions are those relationships that have two properties. First of all, they are, we'll get back. Sorry about that. They are indeed linear, right? So they are going to be linear functions, but they will go through the origin, right? Which is a linear function that passes through the origin. So you know that you've got a direct variation, or you can call it a direct proportion, or you can say a relationship is proportional if two things are true. Thing one, it has to be linear, and thing two is it has to pass through the point, through the point 0, 0. X is 0, y is 0, also called the origin. It too may be increasing from left to right, and then they're talking about something, an activity from the last section 112 that we did not do and we are not going to do, but the one called signing on the dotted line. In that one, you were timing how long it would take you to sign your signature 10 times, 15 times, 20 times. And because it takes you 0 minutes to sign your name 0 times, that one does go through the origin. An example of a decreasing proportion is the elevation of a submarine as it's decreasing. So at sea level, right, at sea level, the submarine is at the origin. And as time goes on, right, as it's diving, as time increases, the elevation below the water level will increase. Okay, so that's linear functions is a big group here. And in our linear functions, we have things that could be proportions, or we can have things that are not proportions, but they both are lines. And it can be increasing or decreasing. Another function family is called inverse variation, also called inverse proportion. The data collected in the hot tub design lab was inverse proportion. This is not a relationship that we study much at all in Math 1, but it's definitely something that will come back, and you'll see in Honors Math 2, 3, and definitely in calculus. But I just wanted you to know that there is this thing called inverse variation. We also observed, although we didn't observe it, was this relationship in something called the flu epidemic, which was problem 11. And this one is exponential. We are going to be studying this a lot later on in the year, but exponential functions have this thing where they have a value where they start, this value right here, and then they have something called a common multiplier or a common ratio, in which you keep multiplying by things again and again and again. So you can consider those names as we move forward today. They may be applicable to some of the relationships that we see and relationships that we graph. So what we're going to do today is we are going to create some multiple representation of functions. Some of these functions may be linear, they may involve inverse variation, and some of them may be exponential functions. So this idea of multiple representation is really useful because when you're looking at a given situation, it's nice to be able to look at the information presented in that situation in different ways. Sometimes an equation's helpful, sometimes a table of data is helpful, and sometimes seeing that table of data graphed on an XY Cartesian plane is helpful. So those multiple representations help us look at data in different ways, look at a situation in different contexts, and sometimes we can gain insight from looking at it in those different contexts. We're going to practice that. So this says obtain lesson 1.1.3a resource page. You don't need this. I'm going to show you the Google slide deck you're going to be manipulating to emulate this like you were in a classroom. So it says study the pattern of tiles for tile pattern 1. With your team, complete figure 4 on the resource page. So let's take a look at exactly what we're talking about there. So this is it. You can see figure 0 has these 3 tiles, and then as we move forward, something appears to be happening. Now, one of the things that's useful is if you're trying to track growth, sometimes look at where you're at and then think, okay, what was added when I went from figure 0 to figure 1. Now I've placed these little red tiles here, and there's a bunch of them, so you can just drag these off and place them somewhere. And if you want to, you could, maybe for this first time, you could just drag these over and say, look, I'm going to put these here. And it looks to me like I can see the original shape, and I can see that I've got these, 1, 2, 3, 4, 5 tiles that were added to it. I can move forward to the next one and you can see that there's more tiles that are added. In fact, you can start to see that if I went from here to the next one, the new red tiles that added would be, right here's one, and then one right here's one, etc. Now, as you're working in Google Slides, sometimes you might run out of these tiles. I put a pretty big stack of them there, but if you needed more, one of the things you can do is you can hold down the Control key on your keyboard and just click and drag, and that's cloning it. So if you start to run out, you can make more of these. Also, you can hold it and you can hit the Control C to copy it and Control V to paste it. So if you find you're running out, you can get some more. But as we're moving forward here, you can see in time we're increasing more patterns. Now, more tiles. Now, what the prompt said was it said with your group, and I realize that you're not with a group, so all alone in your room, I want you to complete figure 4 on this resource page. So if I looked at it, I can see, okay, I've got these tiles and I need to emulate, I need to go ahead and put what I have here, right? And then I'm going to build out and get a whole bunch of them more so I can say exactly what tile figure 4 has. So that's building one representation. You can say it's a physical situation of what's happening here. Another representation of it would be these tiles, and you can see I've kind of completed this. It says figure number 0 and then number of tiles. If you click right here, it's going to allow you to type a number, right? If you click here, you can type a number. Click, click. So most of my sheets like this that you do in slides are going to be set up this way. And the figure 0 apparently has 3 tiles, so you could just put a 3 there and move on. Another representation that we have is a graph, and I have some small little dots here, and I can see that figure 0 had 3 tiles, so I can come down here and I've got one of these dots and go at 0. I'm going to go up to 1, 2, and 3. I can put a little dot there, and if it's hard to get this exactly, say I need to nudge that up, you can use the arrow keys on your keyboard too if you're having a hard time. And oops, that did not move it very well. So you may have to really kind of finesse it. And if you can just get it approximately, that's probably going to have to be good enough, because I can see that it is not wanting to move well, and now it's going to resize it. So go ahead and just put those dots down. I might try to grab another one and put it there on 3. Trying to line it up with the 3. And then figure 1 has another number of tiles, so bring this down and put it on here where that number is at, and then do it for 2, 3, 4, and 5. So fill this out. And another other representation is an equation. I don't think this is a very difficult equation, so you don't need the equation thing that I talked about in class, but you can see this is it. And you can do a lot of equations pretty quickly with this tool. I think on this one you can just go ahead and type like y equals, and I think it's a linear relationship, so it should be pretty straightforward. So this is tile pattern 1, and it says that I want you to complete this in its entirety. And let me come over here and I'm going to flip this live. It does say, and you do not need to have a physical copy of this. It's fine that these are in your Google Sheet. But for question 25, I do want you to come in and in your notebook for 25C, I want you to describe how the number of tiles grows from figure to figure. So as you're going from figure 0 to figure 1 to 2, how does it grow each time? Just describe it in words. And then I'm asking you to describe the graph, and it doesn't say do all these, it just say consider some of these. So if you look at that first graph, what's the general shape of the graph? From left to right, is that graph increasing or decreasing? If you drew a line or curve through the points and extended the graph in both directions, what would be the x and the y intercept? So where would it cross the x-axis? Where would it cross the y-intercepts? If possible, sometimes functions will not cross the x-axis. They can be completely above it. And you can see graphs that don't cross y either. So if possible, what's the x-intercept? What's the y-intercept? And then finally, are there any values of x or y which are not possible in this function? That's just something to consider, right? Not all these are going to apply, but just I want you to do definitely question 25C and question 25D, but all the other stuff you're going to just you're going to set up those graphs in Google Slides. So the intent for question 26A is to get you to look at these things individually. And if you were in class, I'd be asking you to put your pencils down and look at them quietly without working with your group. However, most of you are alone right now and you're working on these alone. So go ahead and look at tile patterns number 2. And then it also says do the same for 3. But for 2, it says, in your mind, think about how you would draw the figure 4 for the tile pattern 2. How would you draw figure 0 for tile pattern 2? And then how would you draw figure 0 for tile pattern 3? So try and just think about those 3 things. How would you draw those before you moved on? And then step B says for each of the following 3, right? 2, 3, and 4. We've already done 1. For 2, 3, and 4, for each figure, complete the tile figures table and graph on your resource page, and you're going to be doing those back over in on slides. Let me go back to that real quick. It's right here. Oops, that's not it. It's right here. There we go. So this is the second one. This is the third. And this is the fourth. So think about these. You'll notice for these 3, the equation is given for 2, the equation is given for 3. I'm pretty sure it is it? Yes, 3. And the equation is given for 4. So you're not asked for that representation, but they are asking you to come up with some of the figure zeros. And notice this one does say figure 0 is undefined, which is interesting. Because it looks like it's 48 divided by 0, and if we take something and we divide it by 0, we do that definition, division by 0 is an undefined function. So for each of these, again, you're going to be completing these values. You're going to be this one doesn't ask you to put any new tiles on. It doesn't ask you to do that, but it does ask you to create the graph, so do that here. This one, there's a pile of tiles here. Do the third figure, do the graph, complete the table. Right here, do the figure 0 and figure 4, complete the table, and then also do the graph. And then finally, to wrap up, what I would like for you to do also, so you're doing 25, the last 2 parts, but also 26, I would like for you to do C and D, 26 C and D. And again, 26D doesn't say use all of these, it's just saying consider these topics, right? Some may apply, some may not. In your notebook, describe how the number tiles of each tile grows from figure to figure for each of those functions, for functions 2, 3, and 4. And then do this where applicable for them. Okay, so that wraps up what you're doing today in class. You're still going to have a homework assignment, and that will be posted. I will be handing out assignment sheets that will have all those homework problems that I'd like for you to do in your composition notebook. You can just keep that list in your comp book, and I'll be checking with you and seeing your progress for those. I hope you have a good morning, good afternoon, and for those of you that are doing distance learning today, remember this afternoon I will be available if you have questions. Have a good day, and I'll talk to you later.